Now, we come next to the iron oxygen hydrogen system. As you know, in the blast air, sometimes you put the moisture, and you would be aware that hydrogen is a more has more reducing power than carbon, and so many times to increase the reducing power of the gas, you use hydrogen. So, either through oil or sometime putting some moisture or water, as we have already discussed about it in the previous lectures. So, iron oxygen hydrogen is also an important system, and how the hydrogen reduce these oxides we will discuss in this. So, as such, so hydrogen and oxygen we had discussed before during the fuel injection lecture under auxiliary fuel. So, we are not discussing this here. So, oxides of iron can be reduced by hydrogen and water mixture like CO2 mixture in the same way. So, main reactions are hematite getting reduced to magnetite, and magnetite is getting reduced to bushite, and then finally bushite is getting reduced to iron, and this is like endothermic reaction, and the overall reaction is given by this equation. So, the different phases of iron oxide in equilibrium with the hydrogen and water mixtures is given in the next figure. So, reduction of FeO, the hydrogen is endothermic, because these reactions are mostly endothermic. So, as you know, the slope of the curves in the figure would be downward. So, the curve inclines toward the downward with increasing temperature, and that is as we said even for when we were discussing with carbon, that slope of this is exothermic. So, it is upward, but for this was endothermic, so it is downward. In the system of iron, oxygen, hydrogen, these reactions are mostly endothermic. So, these are more in the downward direction. So, you can see at 800 degree Celsius or so, there is a hydrogen and a carbon bond line, this is getting intersects. And what does it mean? Because you need a less probably CO below this temperature to reduce the magnetite, but you may need a higher hydrogen potential to reduce the magnetite below that temperature. So, that one can clearly see it. However, at higher the temperature, then you need a less hydrogen power than the CO to reduce the magnetite. So, as the temperature increases, reducing power of hydrogen increases, then the CO. So, here the two curves of FeO reduction with CO and hydrogen intersect around 821 degree, where both the gases have same reducing power over CO at this temperature. As we discussed here, this is about 821 degrees Celsius. However, at temperature higher than this, hydrogen has more reducing power than CO, and at lower temperature it is vice versa. That point again we discussed over here. So, that shows the importance of both hydrogen and CO system and how it could be useful. So, at higher temperature it is much better that, and lower temperature CO is having a more reducing power than the hydrogen. Now, we come to another topic is about the Rist diagram, and these are the graphical representation of heat and mass balances in blast furnace. You know, in chemical engineering you have many of these graphical representation of many processes, even for like Reynolds number, friction factor and like that. So, empirically you can get the values from those graphs. It is similarly in this, same thing is true in heat and mass balance in chemical engineering, and the same sort of principle has been applied here to for this one. So, it is like a graphic representation of heat and mass balances in the blast furnace considering blast furnace reaction. And there are many such diagrams. So, one simple example is given below, which is based on the mass balance of oxygen and carbon, ignoring reduction by hydrogen, dissolution of carbon in hot metals and reduction of other minor oxide except the hematite. So, you can include these ones, you can make it more complex, you can include other reactions, similarly heat valence, and you can then make the diagram more complex and more realistic. But how does it work? That one which is showing it here in a simple way. So, therefore, oxygen input mostly from the air blast which is coming and from the iron oxide whatever you are feeding in, and output is mostly in CO and CO2 in top gas which is going out. So, if we do this in terms of iron, so oxygen associated with the oxide and oxygen in the blast air and the oxygen which is going out in form of associated with the CO2 and CO, and this is the number of moles of carbon which are being input. So, this shows these are the composition of incoming iron oxide and outgoing gases. X is the mole ratio for hematite, which is O2 Fe2O3. So, gives 1.5 for in case of hematite, and this is the mole of carbon input through coke per mole of iron which is needed, and is the mole of oxygen in the blast air per mole of iron. So, all the calculations are based on the per mole of iron, and so the above equation is presented in a graphical form for oxygen iron ratio, oxygen carbon ratio. So, in the upper zone oxygen is removed from the iron oxide. So, this shows a graphical representation, and the slope of this line is nothing, it is this. So, this is essentially this is the line which you are doing this says this, and intercept also you will get it. So, the slope of this line is the number of carbon required to produce 1 mole of iron, which is a coke rate of blast furnace under simplified condition. So, by making it more and more complex, you can then know how much coke is required under that condition, what should be the CO2 ratio and other thing, and more Rist diagram can be made on based on mass balance and even the heat balance you can increase. So, the old time it used to be, even now also at many places they use it, but with the advent of more modeling tool and others, those are much more reliable and important. People are going or going away from these now. There is one example for this. So, a gas mixture of 20% CO 20% CO2, 10% hydrogen, 50% nitrogen by volume is fed into the furnace at 900 degrees Celsius. Find the equilibrium composition of the gas inside the furnace. So, these are the data given. So, carbon plus oxygen, free energy of CO formation, then CO2 formation, the free energy of that, in remember it is given in kilojoule per mole, okay. And then the water formation, this is also in kilojoule per mole. So, based on that we have to find the equilibrium composition of the gas inside the furnace. Now, because there are about 5 chemical species and 4 elements, so we should have a number of equilibria 1. So, we consider the equilibrium this one between these 5 species. So, CO plus water, CO2 plus hydrogen, this is the one. Nitrogen anyway is not going to change. So, this would be the equilibrium reaction, and that we have to find the equilibrium composition. So, the composition of these and free energy, because data are given. So, free energy can be found for this reaction, which comes around 1.6 kilojoule per mole at 900 degrees Celsius, because this is all given at 900 degree, and we have to find the equilibrium composition at 900. So, this is the free energy for this reaction, and if you put it this one, this is in kilojoule, which is will give you about 10 to the power into 10 to the power 3. So, essentially it is not 103, it is 10 to the power 3, and equilibrium constant for this reaction PCO2 PH2 by all in gaseous phase divided by PCO and PH2 as we discussed before in equilibrium, and this can be converted in terms of number of moles. So, that gives you the value when you bring this down. So, substitute universal gas constant and temperature, it will be gives you the 0.85, and also we know the total number of moles in the mixture are these, and then doing a simple stoichiometry analysis for these element for carbon balance, oxygen balance, hydrogen balance and nitrogen balance, this with the nitrogen, that you can arrive with these number, because the percentage and other thing is given. So, you can do the balance of all of these. So, it gives you carbon 0.4, oxygen 0.6, hydrogen 0.2, nitrogen 0.5. So, with the help of these 4 now equations, you can easily calculate in terms of CO. So, carbon so from this you can get the CO in terms of CO2, and you substitute in the other equation. So, finally, you get it your CO2 value is 0.15, because this you substitute back here in this, which is equal to 0.85. So, from that you can get the number of moles of CO2 0.157. Once you get this value, you have to back substitute now into these equations, and here you can get then number of moles for CO from here, then from other equation number of moles for water, hydrogen, nitrogen, and the total anyway will add up to 1. So, total number of moles 1. So, once you know the number of moles, you can convert it into the percentage of the gases. So, CO 24.3 CO2 15.7, water is 4.3 and hydrogen is 5.7, and nitrogen, it does not react, so it would be the same as 50%. So, that would be the composition of the gases at equilibrium.